Okay, great. So let's. The first talk for this session is Mikel Duran Fragola, who will be coming to the stage now, and we will just get his presentation up.
Okay, can you all hear me well? All right. Hi, so my name is Mikel. I'm the lead scientist and co-founder of a small charity called Tercelia Open Source Initiative, dedicated to disseminating data science and artificial intelligence, mostly for antimicrobial drug discovery in the Global South. So the challenge that we are really trying to tackle is what we call the research imbalance, determined by the fact that most of poorest countries basically are affected by infectious diseases, as we all know. But unfortunately, most of the research outcome in the world comes from the richer countries, or so-called the Global North. So there's a huge research imbalance that we should be aware of, and we are trying to tackle this by data science, with data science, because we believe that data science can offer cost-effective solutions to this inequality. So our organization is based on basically 3 pillars. The first is free and open source. This means that all the assets that we develop are free and will always be free for everyone to use. We pursue no patents, no royalties, no revenue from our activities. The central pillar, also very important, is in-country research, otherwise called decolonized research. This means trying to cooperate as much as possible with researchers in-country so that they have ownership and credit and scientific leadership. This means in practice that I have been traveling for the last 3 years, maybe 80% of my time in sub-Saharan Africa. And then finally, third pillar, also very important, sustainable collaborations. This means that we have to build capacity wherever we go because we are small. We will not be there all the time. And it also means that we have to build data science tools that are amenable for low resource settings, so they should work under like very low computational capacity. So basically what we are trying to do is very simple. Is we want to simplify the life of our collaborators and our beneficiaries by basically deploying machine learning tools that we believe can be useful for them. So we do all the boring effort of collecting data, building machine learning models, testing them in the computer, hopefully validating them experimentally as well, and finally deploying them in these outer layers so that they can use them as a software, basically, where they can input, let's say, a drug and predict their targets. That's the principle. What kind of models are we trying to gather? We gather or build models from different sources. Sometimes it's models that we find very interesting from the scientific literature already, the Cell paper from 2020, for instance. Sometimes we build models based on nice data sets that have been published. For instance, this science paper for anti-malarial drug discovery. And sometimes, and most importantly, we build machine learning models in collaboration, ideally with collaborators in the Global South. For instance, happens a lot. This would be the case of a collaboration we have in Cameroon, where we build machine learning models for predicting activity of natural product compounds. So I mentioned before that we are very small, and we are indeed very small, but we try to cooperate with many people. So here you can have like a brief overview of our, I call it, ecosystem. On one side, we collaborate a lot with software engineers and big techs, basically, to gain like the necessary expertise to develop software that looks professional. On the other side, our main collaborators and beneficiaries as well are African scientists or scientists working in Africa. And then we also have collaborations with scientists in the Global North who are akin to us and think like us in the way research should be decolonized, and also with data contributors. So that would be big pharma companies or initiatives that are donating their data to us so that we can model their data and eventually channel it and donate it to the Global South. That would be an example of a center we are working on. That's a picture I took a few months ago in Cameroon. There we are trying to build machine learning models for discovering antivirals based on natural products that they collect from this mountain, basically. We do a lot of capacity building. That's super important. This is a training we did, in this case in Cape Town, gathering scientists from, I think it was 7 countries across Africa. They are all chemists, and they were learning how to use our tools. And now let's go switch gears, I think you say in English, and let's go a little bit into the science, or how do we do it, or how do we make this relatively scalable. So I'm a bioinformatician, so I only understand these kind of things. And so we try to organize all the knowledge that we can gather from our collaborators, but also from the literature, into what we call a biomedical knowledge graph that contains genes at the center, but also diseases, tissues, organisms, etc., and importantly, compounds. So the focus of today's talk is going to be compounds because we are trying to discover antimicrobials, small molecule antimicrobials, to be more specific. And compounds, even if they are small, as we all know, they are very tricky, and they are also very tricky for a computational chemist because they are very difficult to represent to the computer. You can represent compounds with just physical-chemical properties, but you can go really crazy into representing compounds in the 3D shape and also electrostatic shape and all of that, right? So finding the right chemical descriptor is key to have the best possible machine learning models, especially when you are operating in a low data regime, which is our case all the time, right? We don't have a lot of data to train our models. So a while ago, I realized that chemoinformatics has been all the time stuck with this concept of, okay, let's analyze the chemistry of the compound and let's see whether we can predict the activity based on the chemistry. But actually, for many compounds, we know much more if we go to the literature, right? So this arrow here took 4 years of my life trying to understand how we could convert this information that we can find, at least for some of the compounds, into a numerical vector or embedding that we can use eventually for having more powerful and predictive machine learning models. This eventually was published in Nature Biotechnology and is what we called the chemical checkers. So the classical approach to any machine learning in chemoinformatics would be to capture the chemical data of the compounds. Here each row would be a molecule, and this would be an embedding, so the numerical representation of it. Thanks to these kind of representations or extended representations based on literature data, we can collect information about the potential targets of the compounds, networks that might be affected, cells, and also clinical information that would be indications and side effects whenever available. So we believe, and we have shown that using these extended representations, what we call bioactivity signatures, can greatly increase the predictive power of our tools. To show you a visual example, here you can see several drugs from different therapeutic categories, and you can see if we project this into 2D, you can see that drugs corresponding to different therapeutic categories tend to localize in certain regions of this bioactivity space, which makes sense. Therefore, if we come with a new drug and is localized, for instance, here, it is likely to be an antimicrobial compound because this is the cluster of infectious disease drugs. Okay? The same can apply to different metabolites from different species, different tissues and metabolites in tissues and fluids of human, or even food ingredients. So the chemical checker is available for all of you to check it. And here you can see like a very high-level representation of it, kind of representing the kind of data that we are capturing. I think a very important layer is the cells layer, where we're trying to capture morphology, but also gene expression changes for many compounds. Okay, so how is this useful for machine learning? Machine learning, like QSAR, basically is based on 2 steps. The first step is converting the chemical structures into numerical representation that is predictive. And the second step is actually building the machine learning model. So the better you are at this first step, the less data you will need in this second step. That's why we make so much effort in here. These features that you see here would be the chemical checker features in our application. Okay? The idea is that if you can train a model that learns the mapping between the chemical structure and the activity, eventually you can come with a new molecule, represent it, and then predict the activity. We have been doing this exhaustively with our collaborators. I'm just going to highlight here one application. That would be a collaboration we did with the H3D Center in Cape Town. They have about like 13 bioassays that they have been persistently testing over the last 10 years, and they have collected data for 13,000 molecules in these assays. That would be antimicrobial assays, also ADMET assays, and basically some enzymology assays as well. In total, they had 15 assays that they wanted to have modeled. So we did that. And eventually we provided a canvas like this, which I recognize is overwhelming. So I just want you to focus on this plot here. That would be the canvas corresponding to one of the assays, which would be the antimicrobial activity, IC50 in that case, against MTB, this particular strain. And we can show here prospectively that the molecules that we predicted with our score to be more active tend to be more active, right? So this is the kind of validation that matters in these cases to increase the efficacy and the false, decrease the false positive rate of screenings. And they are using this now in practice and in production. However, I've realized the hard way that many times this is not what our collaborators want. Actually, what they want is something like this, right? So they have an activity of interest and they want us to come up with compounds. And that's much more difficult to do, obviously. But this is what we're trying to do. This is overall called generative chemistry, activity-oriented generative chemistry, because you want to generate compounds that are optimized for a particular activity. We've been doing this. Again, this has to be done with low resources in our case, because we want to apply it in low resource settings. This is an example of a generation run that we did for the open source malaria consortium, where given a core of interest, we were generating different derivatives of this branch in a, let's say, hit-to-lead optimization effort. And eventually from this very laptop, we generated, I think it was about 500,000 compounds that we provided to them for exploration and filtering. We eventually selected 8 of them, out of which 4 were deemed to be highly potent, which was very interesting. The baseline hit rate for this assay was 1%, and with the 8 candidates that we generated, we got a hit rate of 50%, right? This is only small data, but that was quite encouraging right in the beginning of our initiative. And we are continuing these efforts with the open source malaria team. So take-home messages. We are Celia. We are a not-for-profit organization aimed at developing AI tools for drug discovery in the Global South. We combine remote work and on-site implementation. We do capacity building activities. Everything we do is free and open source. We offer support mostly to research institutes in the Global South, and we are always looking for data, for contributors, and also collaborators. Of course, we have not been doing this alone. We've been blessed with some funding, but most importantly, with plenty of supporters and collaborators that have been helping us in this journey. So I'm deeply thankful to all of them. And I think that's all. I'm open for questions. Thanks so much.